All right. Well, like I said, I really appreciate everybody joining in. It's like we got the full crew here today,
Yeah.
which is exciting. It's good to have Robert back and then have everybody else kind of join in. So the plan tonight is to finish up the discussion of chapter 18, expressions. So I'm going to cover some of the last bits of that chapter, specifically looking at parsing and deparsing, and then maybe look a little bit at the two kind of examples that Hadley shares, and then like briefly discuss some of the specialized data structures. Really, I think this conversation will probably take 15 minutes. Once we do that, then we'll transition over to Ron, who has graciously taken over Quasiquotation, and we'll start kind of digging into that. We probably won't get through all of that today, so we'll see how far we can get with that. So to get us started off, I just want to do just like a quick review here. Let me share my screen. Share screen, desktop one. Okay, everybody can see my notes, right?
Yes.
Sweet. All right, so I just wanted to quickly kind of review like where we were at with some of the learning objectives. We were kind of finishing around this kind of learning objective here where we wanted to explore the idea behind parsing and deparsing. And then we were also going to look at looking at using recursive functions to compute on the language. And then we're going to finish up looking at some of those three or more specialized data structures, specifically pair lists, missing arguments, and expression vectors. And so before we kind of dig into that, I just want to do like a quick reminder of why we're talking about expressions. It's really this quote in the book that really emphasizes why we need to understand this stuff. And again, it's this idea that to compute on the language, we first need to understand its structure. And that structure is based on expressions, which can be represented as abstract syntax trees, which we dug into pretty extensively last time. And as we've been working through the chapter, we've been talking about each one of the components of an AST and how they're represented within the AST. And we were kind of getting into the point where how we can use that AST to compute on the language itself. Again, because the language is data, and so we can compute on that data. And so a really kind of interesting discussion that we've been having around that. So we finished with associativity last time, and we were talking about that R was left associative, except for two very specific cases. So the two cases where there is an exception to being left associative is in exponentiation and then assignment. And so these are just different rules that R follows for the evaluation of different infix operators. And so we kind of left off with that discussion. And then we started moving into the idea of parsing and deparsing. And so parsing is just basically the idea of turning characters you've typed into an abstract syntax tree. Now, we didn't have to really think about this, especially when you're doing like interactive analysis or you're creating scripts or you're writing stuff, because R would just handle the parsing for us. But now, because we're trying to compute on the language itself and compute on the abstract syntax tree, we need to understand how this parsing portion actually works so that we can get the best out of metaprogramming. And so occasionally what we're going to want to do is we're going to want to have our code stored as a string, and then we want to parse it ourselves. And rlang provides for us this function called parse expression, which will take a string value and turn it into a call value. And so, or we'll parse it into an expression. So in our case here, we just have the string value of, we're just associating x plus 10, giving it the name y, or associating it with the name y, and then we're just checking if it is a call. It is false. So if we want to turn this into an expression, we just need to plug it into parse expression, and then it will turn it into a call, and you can double check it right there if you want to. Big thing to remember is this is great if you have a single expression, but if you want to parse multiple expressions, you need to use parse expressions. So if you have a string value that has two expressions in it separated by like a semicolon, you can still parse that into an expression. What's interesting about this is that when you parse these expressions, it basically acts like a list. And so you have your first expression, this value 1 being assigned the name A, and then this operation of a plus 1, it's pretty much like a list object now once you parse it. Now, the book says that you can do this, but it's highly suggested that if you are going to do this a lot, you probably should look at doing quasi-quotation, which Ron will talk about here in a little bit. The inverse of parsing is deparsing. So if you want to go from an expression to a string value, there is an rlang function to do that. It is expression text. So basically all you need to do is you have your expression. In our case right here, we have this operation x plus 10 getting assigned the name y. We wrap it in expression to capture or to create the expression itself and assign the name z. If we want the text value of that to return the string, you just wrap it in expression text. I don't think there's anything too crazy going on here. It's just mainly the idea of going from a string value to an expression and then back from an expression to a string value. Nothing too crazy that's going on here. Now, the book goes a little bit further and it kind of gives 2 examples here of how you can use the AST to solve some more complicated problems. And really what we're going to focus on here is learning how to perform recursion on the AST. Now, I wasn't as familiar with recursion, and so I'm sure there's people here that would be more familiar and better to explain this than I will, but I'm just going to kind of walk through like the bits and components that like Hadley did for each of these examples and talk about how each of these examples solves for the recursive case and the base case. Now, because I'm not totally familiar with recursion and recursive functions, this part kind of went over my head. I kind of understood it in the context of the examples, but in a broader context, I really didn't have the background knowledge to really understand what he meant by base case and recursive case. So if anybody can fill me in, that would be greatly appreciated. And really with these 2 parts, they correspond well to the tree-like data structure provided by the AST. And so to kind of get us started off, Hadley talks about that if we are going to do this, kind of creating these recursive functions, what we need to, or these recursive functions that are going to compute on the abstract syntax tree, we need these 2 helper functions. And so basically what Hadley is doing here is he creates 2 helpers. One, this function called expression type, which uses a bunch of if-else statements to basically identify what type of component is in the expression that gets passed into this function. So basically you can see all it's doing is it's just checking for what component of the expression is getting passed into this. So you have a constant, symbol, call, pair list, so on and so forth. So here's the example with this kind of helper function. When you pass these values in from these expressions, you can see it identifies this a string as a constant. It identifies this x as a symbol, and then it identifies this expression f as a call because it's a function call. So the second thing that Hadley does is he creates this wrapper function. And so I think Hadley really likes wrapper functions. He really, really likes wrapper functions. And so I think that's where it kind of gets confusing to me, is this idea of like you're wrapping functions inside of functions. But basically all this is doing is it's wrapping this switch statement and it's creating another switch statement that's handling exceptions. So if for some reason you're using this function and it passes in an object that is not of a type for an expression, it's going to stop and just throw an error. So this is just another wrapper function around that. And then Hadley creates another one called recurse call, which is just another switch statement, which is going to help us handle the base case and the recursive cases. So in the cases where if things are identified as a symbol or a constant or a call or a pair list, we get to decide how we want to compute on those elements. And so we'll be able to write the functions or however we want to address that. And so basically these next 2 examples that Hadley talks about utilizes these 2 examples, are these 2 kind of helper functions to help out with writing recursive functions that compute on the AST. So does anybody have any questions about this or comments? To me, it seems pretty straightforward, but did I miss anything, or does anybody want to add any additional context to what's going on with these helper functions. All right, sweet. So going from here, the Hadley kind of takes this recurse call function that we had, and the first thing he's going to try and solve is trying to find f and t in expressions. And so basically what Hadley wants to do is he wants to create these recursive functions that compute on the AST to identify any times that we use f and t in our code. Mainly the kind of motivation to do this is because it's bad practice to use f and t, and rather we should be using false and true. And so what Hadley wanted to do is he wants to show how we can use a recursive function to compute on the AST to figure out, okay, where in our expressions are we using this to potentially flag situations where we might want to change it. So when we do this, we have to kind of first find out, okay, what type is true and the value t. And so when you look at this, when we run on an expression type expression on this value of true, or this value of true, it's a constant. And in our case here with just the letter t, it's a symbol. Okay. And so with this knowledge, what we can do is we can write the base cases of our recursive function using this kind of logic. And so Hadley kind of writes out the logic like this. A constant is never a logical abbreviation, and a symbol is an abbreviation if it's false or true. And so what we can do in our logical abbreviated recursive function, we can add it in our switch statement to say, hey, if it's a constant, it should just be false. And if it's a symbol, turn it into a string, and then determine if it's a symbol that's an F or T string value. Okay. And so basically, if we take this and we look at it, we can see the base cases are accounted for, because when we pass this expression true, we get the value false. And then in our case, if we see an expression t, it becomes true. And again, if we are using the t in our expression, it's going to flag it as an issue. So the Hadley, again, creates a wrapper function around this, because we would make the assumption that anytime that we pass an input into this, it's going to be an expression. So we might as well just convert everything into an expression. And so he just kind of simplifies this into this function here by just like wrapping it in expression and then calling our function that does all the switch statements. And so in our case here, if we pass the value t, it's going to be true. If we pass in the value false, it's going to be false. So the next part is that's the base case. Now we're going to solve for the recursive cases. And so with the recursive cases, Hadley suggests what we need to do is we need to account for certain things. So we need to look at this in the cases for calls or pair lists. And how we're going to do that is we're going to recursively apply a function to each subcomponent and return true if any subcomponent contains an illogical abbreviation. So if for some reason inside of our function we use a T or an F, it will flag it as true. In cases, and then we can also simplify this by using per sum, which basically says it's going to iterate over that list and return true if any of those elements are true. So if you have a list and any of those elements are true when you're actually checking it, it will just return one true or false, because that just makes sense. Because if you're using one F or T, then you want the function to return that, hey, there is an issue in this code using the letters F or T. Okay. I was a little confused at this point right here of why we're using logical abbreviation. I think it's abbreviation abbreviation recursive here, but I think I kind of figured it out, because it's mainly because we want to use that switch statement to make sure that we're not using that T or F, even if it's like a pair list, because more than likely that pair list is going to be the set of arguments inside of the function.
Yeah. Could interject here, I think, Colin.
Yeah, go for it, please.
Because I think this comes back to the fundamental methodology here of doing the base and recursive. So the idea of writing a recursive function is you make a decision. Is this the base case or the recursive case? The base case, I know how to handle immediately. Okay. I know immediately if it's a constant, it's false. If it's a symbol, it's F or T, then it's true, and I'm done. I'm done with the whole thing. I pass it back up, right? On the recursive piece, That's where you have something that's got parts to it. And now I got to call recursively the same function on all the little pieces and then combine them together somehow. That's the recursive part. So the fact that logical abbreviation recursive is there is actually part of the defining characteristic that makes this a recursive function to begin with, right? Because we're calling the same function, because you can look at it this way. Look, now I want to find out if any of these parts have any logical abbreviations. Oh, I wonder how I can do that. Oh, wait a minute. I have a function that can do that. I'm defining it right now, but I can still use it. Just put it in there, right? That's what's going on.
That makes a lot more sense, because every time I think of recursion, I think of iteration. Like, are those similar?
Yeah, iteration is like unfolded recursion in some sense, but yeah.
Okay.
Like you've probably seen the usual factorial function defined recursively, right? The base case is if n is 0, I know the answer is 1, right? Mm-hmm. If n is not 0, then I know how to get the answer. Just take n and multiply it by the factorial of n minus 1. So I have to use the same factorial function again. It's the same thing you're doing here, just now we're doing it on data structures.
That makes sense. So it's like the constant and the symbol. So the base cases are like, I have one value.
Yeah.
Right. But then like calls and pair lists, there's multiple components. Yeah. Oh, okay. That makes sense. Because the leaf, there's only like one leaf, but there could be multiple branches.
Right.
Oh, okay. That makes sense. Okay.
I hope that helped anyway.
Yeah, no, it helps me a lot, because like I've never been, I've heard of these idea of recursive functions, but I've never really like understood, like when I was looking at these examples, I was like, what does he mean by base case or recursive case? But it makes sense where you're saying like base cases are like, there's one thing, right? And so it could just return it immediately. Recursive cases is like, it could come across, it has to like compute on many different components of it.
Right.
Okay, that makes sense. All right. And that's where it comes in with this like per sum. It's like it just wants to identify, it's going to go through and compute all the cases.
For all the leaves, but for all the branches, which could be branched all the way down to, it may take a while to get to leaves, but at some point it's going to get to the base cases and propagate back up.
Oh, okay. That makes a lot of sense now. Okay, yeah. Now I'm getting it. I would
say like a factor for recursion is that the recursive function will always, every time you call it, will drive your value to the base case. So no matter what, you'll get there eventually. It's just a matter of it figures out how many times it needs to call itself before it gets to the base case and then reassembles it all the way up. So like for the factorial example, you're always going n to n minus 1. So you're always reducing it. You're always at least getting down to the base case at least one step at a time. And eventually you must get to the base case. And then you know how to solve the base case, and then you reassemble the very top. So the base case is like, you know the answer. The recursive case says, eventually, if I call enough times, I'll get to the base case, and then I can reassemble myself.
Okay. Because if you didn't solve for the base case, would you just find yourself in an infinite loop?
Yes. Yeah. And that does happen with badly designed recursive functions. You're not careful to do what Stone just said. Make sure that each case gets smaller in some sense, or goes toward the base case.
You have to guarantee that you'll eventually hit a base case, then you know what the answer is.
Okay, that makes sense now. Okay, that makes a lot more sense, because I think Hadley in this part of the book, he just assumed that you knew what recursive functions are and understood like if you're going to build this, you need to know what the base case is and what the recursive case is, and I didn't. So I was just like, okay, I'm going to try my best here, Hadley, but now it makes a lot more sense. Like it's just basically iteration over the AST. But if you don't solve for the base case, then it's, you're going to get into a potentially infinite loop, but you always have to like iterate over those components. There's portions of your expression that you may have to iterate over, and that's where the recursive case comes in. Okay, that makes sense.
Yeah.
Cool, appreciate it. I think that actually helps me a lot, actually, so I appreciate that. Oops. Okay, so this is a pretty straightforward example, but Hadley says, okay, there's more kind of a more complicated case, and this second example is this idea of finding all variables created by assignment. And so basically what Hadley wanted to do is, in this example, he wants to list all the variables. So listing all the variables is a little more complicated. And so what he wants to do is he wants to find any time that something is assigned within an expression. And so he kind of walks through this example of like saying, okay, first we have to look at, well, what does it look like in the AST for assignment? And so here's basically the basic example of assignment. We obviously have this branch, which is a call to this infix operator of assignment, and then the symbol X and this constant 10. And so what we need to do is we need to first decide, okay, what data structure do we want our results to return in? The easiest thing that Hadley suggests is to return it as a character vector. But if we wanted to return symbols, we would need to consider using a list as our data structure to return the data that we want after we get done recursing over the AST. So first thing that we've done before, we deal with the base case. And so we start here creating this find assigned recurse function, where again, we're going to use switch expression, looking for constant, and then the symbol character. And then we're just going to just wrap it in this find assign recursion, creating an expression again, mainly to simplify it, because we would want any time that somebody passes any values into it, we want it to be an expression. So this is just a wrapper for that. And so in our case here, if we pass this X, which is just a constant, we'll get character 0, which makes sense. And then if we pass in this symbol, we'll also get character as well, which is character 0. So Hadley talks about, okay, we're dealing with the base cases. Now we need to do the recursive cases. And so Hadley suggests that we need to create this function combining both flat and character and per map to create a flat map character function. And basically all this is going to do is it's going to take an input, and all it's going to do, if I remember this correctly, it's just going to sample each component of it. No, wait, actually all this is doing is it's repeating a sample of letters, and then all of it's doing is it's just repeating that. So here, if we do A through B, it's going to go A, B, C, so on and so forth, I think, right? But anyways, I think he's just showing the example of like, what does flat map character do? It's going to take an input and return a character vector that's flattened rather than being some type of list. So what we're going to do is we're going to use this function to identify any of the calls that we have. And so in our case right here, we're going to use the recursive cases. If we receive a pair list, it's going to go through all of the components of the call and return it as a flattened character. And then any call that we have, we're going to look for any assignment. So if it's assignment, we're going to do some subsetting to it and turn it into a string, or we're going to return all of the elements of the assignment in this else statement. And so if we start here with our function find assign, where we're assigning this value 1 to the name A, we'll get this value string A back. If we do this twice with the nested assignment, where we have we have 1 being assigned to the value of A, or 2 being assigned to the value of B, it's going to return 2 symbols, or 2 strings, which represent symbols A and B because of the assignment there. Hadley wants to go one step further. He says, great, you've done the recursive case and the base cases. Let's throw some other stuff at it to try and break this function to make it more robust. What he wanted to do here, and this one gets a little bit beyond like my knowledge set, but basically it's like the idea of what happens if we have multiple assignment, and how does your function assess for that? And so basically that's what Hadley is doing here, is he's just writing out some functions to account for multiple assignment. And so I think for the sake of time, I'm not going to dig into this, but you can kind of look in how he kind of implements this to make it more robust. But the one thing that I really wanted to get out of this was the idea that, you know, it really starts off small and then it builds up to like a more kind of complex thing. And so it really starts with like a very solving for like the really simple cases and then making things more robust. So does anybody want to add to this example? I know I kind of like briefly went over it, but I kind of struggled when it got to this more robust definition of trying to find all assignments, especially if there's multiple assignment. Okay, cool. Let's move on to the last part, which is just the specialized data structures. There's 3 of them: pair lists, missing arguments, and expression vectors. Really with pair lists, these are basically been replaced pretty much everywhere, and lists have replaced them. But there are still some places where you might come across pair lists, and they mainly come when you're dealing with like formal arguments to a function, because those are stored as a pair list. So we have this anonymous function here that's being defined in this expression. If we subset this out, this expression here, the second element, we're going to get kind of this list kind of thing, which is like value X and Y. And then if we look at two of these, we're going to see it's a pair list. And so, but the book basically says whenever you encounter a pair list, just treat it like a list. And so you can do standard list computation on it. So if we create this pair list here, we can check the length. It's going to give us 2. If we want to subset, we can use $sign to subset out that X element in the pair list. So nothing too crazy about this, but basically, like if you do come across a pair list, no, it's like a list. So missing arguments is another thing that the book kind of talks about. These are just empty symbols.
Are we to understand that pair lists are basically just an ordinary, linked list type thing? Is that what they are? I didn't quite grok what he was trying to suggest there with the pair list.
I'm not sure. Does anybody else have any idea? The way I understood it basically is like you're only going to come across this when you have like formal arguments within a function, but how that actually works, I'm not 100% sure.
Yeah, they are linked lists. I just looked it up. So the name is suggestive, pair list. It makes it sound like there's a pair, right? So there's a head and a tail, and then the tail has a head and a tail, and head and a tail all the way down. Linked lists.
Okay.
I'm doing a terrible
cool.
job explaining it, but yeah. Sorry for the interruption. That just drive me crazy.
No, it's good. I mean, like these components I've never been introduced to, so I'm not 100% sure like how the pair lists work outside of like, hey, it's just like a list. You can check the length of it. You can subset it just like a list. So it doesn't have like anything like special behavior, at least from what the book says. So missing arguments, these are just basically empty symbols. If we want to create empty symbols, we need to use this rlang function called missing arg, or we can go back to expression to use this. And so what you can do is you can do missing arg, which if you do missing arg right here, it's just going to be a symbol element. Just know that if you do create an empty symbol, it doesn't print anything. So if you want to check if you have a missing element, rlang provides this convenience function called isMissing to check if it's true. And so if we pass missing argument, isMissing, it is true. So usually these are in function formulas. So basically, like if we have a formula inside of a function or an expression, and we want to capture those arguments by subsetting this expression like this, if we wanted to check if this was a missing argument, we could pass it into isMissing, and it will tell us if it's true or false. The last kind of special data object that was out there is this idea of expression vectors. So an expression vector is just a list of expressions. The only difference is that when we call eval on an expression, it evaluates each individual expression. Now, Hadley says you can use expression vectors, but it might be more advantageous if you just use a list of expressions. So, and I'm not 100% sure why this is rendering this way, but basically this was supposed to be inside of this character vector here. But basically you can use two functions to produce expression vectors. You can use parse or expression in itself. I can fix this later. But basically, if you do this, and it looks like I actually have an error in here, or you can use expression here. We have X, or we have value 4 being assigned to value X, and then X turn into an expression, and then we can check the type of, and you can see it's an expression. But it looks like my kind of notes kind of misrendered here for some reason. Just like calls and pair lists, expression vectors behave like lists. So same thing, you can check the length of it, you can subset it. And obviously I'm having an error here right now because I think I accidentally misspecified it in my notes, but basically they just have the same behavior as the lists. So I know that was that took a little bit longer than I thought it was going to take, but that is pretty much expressions. What comments or questions do people have, or further discussion that they would like to have about expression components, or anything that I missed? I mean, just kind of like to summarize, I think it's really knowing the structural components of an expression and an AST, and that you can compute on them was what this whole chapter was about. Nothing that was like overly exciting, but it's important information to know, especially if you want to compute on the language as if it was some type of data that you wanted to use. So cool. If there's no other questions or other further discussion for this, I think we can take the next 25 minutes to start kind of diving into chapter 19. Ron, you were going to lead us in 19, so I'm just going to turn it over to you.
Okay, I will do the old screen share. There we go. Let me just move this over here where it's in front of the thing. Okay, you can stop with that. Sorry, I gotta always reorganize things. Okay, you can see the notebook now, I assume. Very good. So this is chapter 19. I actually think chapter 19 is, in my mind, is a little bit more straightforward than chapter 18. I don't know why that is, but chapter 18 was quite a bear. This chapter is on quasi-quotation. So the objectives here are to understand what quasi-quotation, what does that word mean? Why is it important? And then we'll find some practical uses of quasi-quotation itself. So this part of the book is actually really about tidy evaluation. This is the topic, and there's three legs on the stool of tidy evaluation. One of them is this chapter's topic, quasi-quotation. And in chapter 20, which I think Ryan has signed up for, on evaluation, we're going to finish tidy evaluation and learn about closures and about data masks, which are the other parts of the tidy evaluation picture. So what is quasi-quotation? And what it is simply quotation and also unquotation. Quotation we know about, we've done that before, is capturing unevaluated expressions. And in the R documentation now, it calls this diffusing. This term is not used in this advanced R book. Probably like in the next edition, he'll start using it because it seems to be a change of terminology there. And then unquoting, and unquoting is kind of the opposite of quoting, but it's usually done like inside of a quote. So you have something quoted, but you want some parts of it not to be quoted. You want to evaluate some pieces of the expression. And that's being called in the documentation currently injecting, which makes sense because you've got something you've quoted, you've diffused, and then inside there's some piece you want to inject evaluated parts to put into that abstract syntax tree some specific values, either other trees or actual value or constants. So any functions that use these features that we've talked about before, that's called non-standard evaluation. So all this section of the book is about non-standard evaluation, and tidy evaluation is kind of a tidy way of doing non-standard evaluation. I do want to add a note here that came from the book that this is related to this concept goes back earliest to almost early days of computing and programming with list macros. They've had quoting and unquoting, very similar actually to the way it works in R-lang. And other languages with that kind of heritage also have this feature. I call it just the one Julia, since that's something of some interest to me. I want to learn how to use that. So I'm glad to see that Julia has some of these features. Someday when I get to that part of my to-do list and learn Julia, I'll remember that, hopefully. So as a motivating example, the book gives this concrete example with this function called cement, which I don't know if that was intended to be funny, but made me laugh. And the function cement the idea is, oh, I'm doing a lot of these pasting and I have to keep putting things in quotes all the time. Is there some way I can avoid that? Well, we can use quotation to avoid that. So this function cement takes its arguments as 3 dots and turns it into an expression or a list of expressions using in sims, which is just like an expression, which you already learned before, but in sims, make sure that the things you're turning to expression actually are symbols or strings, symbols or strings. Okay. And then all we do is use per map here to turn those symbols into strings. And then we call paste, which is the function we're trying to mimic. And so we can say, oh, good. Now cement together good morning, Hadley. We get good morning, Hadley. It works as we expect. We don't have to put the little quotes around. So that's good. But now, wait a minute. What if I did want to use some variables? Well, if Hadley was a variable, it's still going to think it's just a symbol. It's still going to turn to a symbol and it's still going to say good morning, Hadley. So for example, I have a variable named name. The way you do that is this injecting with 2 exclamation points. That's the unquote operator. So I can say good afternoon, bang, bang, name, and then I've got good afternoon, Bob. So that injects the actual value for Bob instead of just putting the symbol name into that abstract syntax tree, and then finally evaluate it in the paste function. So that's the motivation. That's kind of the quick introduction to what the unquoting part of quasi-quotation is. And that's the syntax, basically, this bang bang thing, or I think it's, if you look in the R documentation, it calls it the inject operator now. It's the inject operator. So this kind of non-standard evaluation that was just demonstrated is used quite a bit in the tidyverse, as you're probably aware. For example, when we call a function like dplyr filter, we don't need to put in the full variable name. We can just use, like it shows here, dplyr filter, empty cars is our database. We can say, look for all the things where cylinder equals 4. Well, cylinder is not really a variable in our global environment. So if this was evaluated as immediately before being called, it wouldn't work, right? And so you can often detect it by doing that. For example, when you also, another one with non-standard evaluation is a library function. You don't have to put quotes around mass because it does some non-standard evaluation so you don't have to do that. And you can detect that by just typing in mass on the command line. It'll say, oh wait, error object mass not found. Well, that's interesting. How did I pass it in then? Right? Because they're doing some non-standard evaluation. That's all the point of that. Same thing with cylinder. You type in cylinder, obviously that's not going to work because it doesn't exist. It's only part of the data frame. And of course, this is really the idea of data mass, which comes up in chapter 20. So going back to quoting, this is kind of a bit of review since we've done most of these before. We know that at the interactive level, we can just use the function rlang expression, x plus y, for example. We just get the expression back as an expression object or call object in this case. An n expression is when you use inside of a function to capture the arguments as expressions, unevaluated. To capture multiple arguments, where you can use n expressions, is usually used with the triple dot notation like this, a dot, 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 to capture all the arguments. For example, here it is. It's just the arguments unevaluated. See, 10 times these unevaluated. These are all unevaluated. We've held the evaluation, so to speak, by capturing them. And then, as I mentioned before, there's also a form called nsim and nsims, which is similar to an expression, but checks to make sure you have a symbol. I think the reason for that, maybe he says, and I forgot, but right off the top of my head, the reason I think that's important is you want to just make sure that the function is called the way you expect it to be, maybe for safety reasons, and also because maybe the rest of your function assumes that they're symbols, and it would fail badly if you just use an expression there. If anybody has anything to add to that, I'm certainly willing to hear it. So that's oh, then there's a little bit of an aside here about the base R methods for doing this. And I'm just going to kind of brush through a lot of the base R stuff because my brain can't hold all these ideas in my head at the same time. So I'm glad to know there are base R methods, but I'm not going to pay a lot of attention to them. These base R methods don't do quasi-quotation because you can't unquote them generally. You can use quote at the interactive level to capture an expression, and inside of a function, you can use substitute, which actually does a little bit more than just an expression does. It actually does let you substitute in values, but it is a way of capturing an expression that has been passed into a function. And interestingly enough, an expression uses substitute, because after all, I looked into this like, well, I know it's a C code function in the end that's being called for an expression because there's a lot of work to be done. to capture all these unquoting things. But I was wondering because like I know there's no way to actually hold an expression when you call a C function. So now I found, oh, I see it. So it uses substitute inside the definition of any expression. This is it. This is the whole thing. That's all it does. It just substitutes the arguments and then calls some C function, which really was where the real work is being done. And Hadley hints at in the book here that was a hard problem to solve, to get all that to work properly. Because one thing I didn't mention here, but he does mention in the book, the bang bang and the bang 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 operator are not like normal operators in any sense of the word. They don't exist as actually operators in the syntax of the language. It's all done inside these in the C code.
Hey, Stone, is Ron like dogging like some base R stuff? Is it like, does that like set off some of your like?
I'm not dogging base R.
With your New Zealand history, does this like his giving short shrift to base R? I don't know, man.
This is one place where I think base R is deficient.
Yeah.
I think I might be recalling this incorrectly, but I think Lumley did write B-quote though. So
right. So, oh, did he? That's funny. So
I'm teasing, of course, Ron. Sorry, I just was.
No, it's not me dogging base R. It's me dogging my own inability to keep all these ideas on, in RAM at the same time. So as I get older, that RAM capacity continues to decrease too. So B quote is, you just mentioned, that's a base R form that does provide some limited form of quasiquotation. I didn't put that in these notes again for the same reasons I just said, but it's in section 19.5. So, Stone, you may need to read that to do some quasiquotation like things. But and then finally, the twiddle thing, the formula thing, is also a quoting function. That we'll discuss in a little more detail in chapter 20, or his claims. I didn't look, but he said. Let's see, where are we at? Unquoting. So this is the injecting, the unquoting. This is an operator, quasi operator. I don't think it's called that. I shouldn't say that. Pseudo operator, better to call it that. That allows you to merge together different abstract syntax trees, right? Using the selective evaluation. He gives an example here that if I create an expression -1, I can also just write x equals -1 here, but I want to make an expression where the -1 is actually pulled out, right? As an operator. So it's actually a call expression. And then I'm like, oh, I want to combine that to this other expression I have, which is f of x and f of something and y. I can glue in the something by injecting it with a bang bang x, and it will do that. And I can look at the expression with lobster, and there it is, right? It's f of, -1 and y. It worked, right? By the way, there's another use of injection right here. I just snuck that in. This is an example he brings up later, but if it often may happen, you have an expression you created somewhere else, but now you want to look at the abstract syntax tree. In the last chapters, we've always just had to rewrite the whole expression again in here, but now we can just use the injection operator, bang, bang, res, as it were. That's why I called this thing res. And you can get the abstract syntax tree diagram just like that. Kind of cool. Let's see. Another thing that's kind of cool is that if the right-hand side of bang bang is actually a function, it will call that function, and whatever comes back from that function will then get inserted in. So when you see this bang bang mean of x, it actually calls mean of x, or whatever x is. Whatever comes back, that gets injected in. That's kind of cool. It's not immediately obvious when you look at it that that's what should happen, but that is, I guess, the way it's been defined, right? I don't know if I want to say. Is there any question about that? Should I say something more about this? It's just something you have to like stare at for a minute to see what it's doing. But
I guess I'm like trying to like walk through it here.
Yeah.
So like,
yeah.
Okay, so you have this function mean rm. You pass in a var variable into nsim, which is just turning it into a symbol, which is var. And then you have bang bang, which will unquote it. So would unquoting basically mean that it would evaluate it at that time once you do bang bang evaluation, or?
No, it'll inject whatever that symbol is there at that point.
Okay,
Yeah.
inject. And then we capture that expression, which would be mean, whatever we defined our variable was, and then we unquote it here in the mean RM, which would just be mean of x na.rm equals true plus the mean RMY.
Yeah.
Oh, okay. So it's just basically like, it's like just injecting that function, the call itself.
Yeah, right. The results of that
Okay.
call, right.
Okay, that makes sense. Okay. That makes a lot more sense now, because it's like the idea of injecting makes sense with a variable, but when you start thinking of it like a function, that's where it gets a little messy for me. But it's just injecting those components of that expression into that abstract syntax tree.
Yeah,
You know?
exactly right.
Okay.
And then for multiple arguments, they have bang, 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 which will allow you to shove an entire list into the arguments, for example. And this is now called the splice operator, which is something, he does use the word splice occasionally in the advanced R book, but he doesn't call this the splice operator, but that's what they're calling it now. If you look up, if you do question mark, bang, 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 it'll say, this is the splice operator. So that's the terminology that's been adopted now. And the way this works is if you have a list of expressions, right, you can insert that list with bang, bang, bang. Right. If you just did bang, bang here, you end up with a list here, but bang, bang, bang flattens it out in some sense, right? Puts each element in there one after another and splices them in. I guess splice is a great word for it. That's exactly what it does. So for example, when we did this right here, we have this expression 1a minus b, and I'm going to splice it in comma with y at the end there. It's spliced in. Notice there's no extra parentheses here. It's been spliced in flattened like that. And we can look at the abstract syntax tree and just verify, yeah, it's been flattened.
So that's putting in symbols and
Constants, yeah.
Symbols and constants. Could you do the same thing with calls?
Yeah, you can put it, yeah, you can. One of these things was a call, it would be in there too, just as well, right? But this is more commonly used for the ... case, right? Because the splicing operator is very useful in places whenever you have like a list of expressions that you want to insert into a call, which is something that probably happens quite a bit. You got a guy with this list of options. I want to just put that in there. In Python, you can do that with keyword arguments, and he mentions another language you can do with it's called splatting, I guess, in Julia. This is the one of the main uses of this kind of ... thing. Outside of the quasi-quotation, it's almost like outside of the quasi-quotation in some sense. It's not like we have an expression we deal with. Now I just want to shove in arguments into a function. We're not necessarily going to be in simming or in expressing them or anything like that. So he gives two kind of examples, which I probably should have started with before wandering off beam there. One is example if I have a list of data frames and I want to R bind them together. Certainly this particular case, I just have two of them. It's pretty straightforward how to R bind them together. But if I have many many of them, it's not quite so clear how to do it. And another case is what if I want to have an argument name, but I want to supply it indirectly. I storing the argument name inside of another variable that I'm going to use. I can't think of why you want to do that necessarily, but if you did, there's a way to do it, right? For the first one, it turns out you can just splice it right in. Splice in the data frames into bind rows, and it just works, right? And you can see how it can work because when I do the bang, bang, bang to this list, right? It's just a list. So it's going to put in A, B. Now it's going to say bind rows A, B. And if it was more, then it would say bind rows A, B, C, D, whatever it was, right? And bind rows can work with any number of arguments. So it works perfectly correctly what you expect. Like I said, it's just called splatting in other languages, but here we're calling it's called splicing, which I think is a better word anyway. Splice away. For the second one, we need another operator, another tool, because if you want to unquote we want to be able to unquote the left-hand side of a equals symbol inside of an argument list, right? You can't do that the equals sign is built into the core of the way R parses functions arguments. So the tidy guys had to invent a new way to do that, and they invented this operator colon equals, what you use instead. And if you use colon equals in one of these tidy functions, it will work. You can unsplat, you can splice in or inject, in this case, your var, and just use colon equals instead of equals, and it will work as you expect. So I do Tibble, var equals val, it'll evaluate x is equal to these three things. Remember, val, this is my column header, and this is my value. I guess that's one good example when you may have variable names that are column headers you want to be able to use, right? So that's how you do that. And this whole capability of all these tidy functions is called in the book tidy dots. Again, it's something they changed now, and all the documentation is called dynamic dots, which actually is a lot cooler sounding. They're dynamic dots. So this last section of the book is all about how to bring in tidy dots into your own, which is the primary use of quasi-quotation on its own. Now, of course, there's lots of uses we're going to probably find out in chapter 20 for quasi-quotation in the full tidy evaluation picture. But even just using quasi-quotation in this tidy dots, it does enable you to do a lot of fun things. Now, with that being said, it is 8 minutes till 3. I don't know whether we should, I don't know if I can get, I don't think I can get through it all, the ... stuff. And rather than trying to rush through the ... stuff, I just laugh at myself because that sounds funny.
Yeah, let's take some time next week, dude.
Yeah, if that's okay with you, Ryan, because you're going to be doing the evaluation part. I'm going to be stealing some of your time. I don't know how we can get back on track on this. We're going to be doing these things. But...
There is no track, and this is complicated stuff.
That's
so
true.
If you have to take more than 1 week, it's fine. Don't worry about it. So you think how much? You think you might need half of next time? Just, I mean, I know it's
no, I don't think so. I just think maybe it's like a 20-minute type thing, 15 to 20 minutes. I don't want to just like trying to crunch it all in because people might have questions about how these things work. And
yeah,
I do.
No, that's fine.
And I do too.
Yeah, I'll be ready, but let's plan on it being, maybe up to half the time for this. That's fine.
Yeah. So next time I'll pick up on the ... where I'm at right now. Well, I'll pick up on list 2, I guess, which is how you use ... in your own functions, which is really kind of fun stuff. There's some fun examples at the end of this chapter of things you can do with that, with the quasi-quotation and injecting with and splicing with list 2.
Absolutely.
Dynamic dots. That's
dynamic dots.
More dots.
Absolutely. More dia. Yeah, I think that's probably a good plan moving forward. Like I said, there is no like standard track for this. So it's like if things definitely take longer, like we can definitely take more time. Like we're not pressured on a deadline to get the book done. So
right.
Yeah, so I think what we'll do is we'll devote half the time to 19 and then the other half. And I was just looking at evaluation. Evaluation is pretty extensive, so that could be almost 1.5 itself. So that could be a 1.5 itself. So
that'll get us back
don't worry about we might actually get back on track. So I think if we can finish up quasi-quotation next week and then at least talk about evaluation, get that started, I think we should be pretty good and see where we're at. And if we have to reconfigure the schedule, we sure can. So all right, cool. Well, I really appreciate
I say we're going to be pushing chapter 25 into the middle of when I'm going to be traveling, potentially. I guess we'll work out when we get there, but looking ahead, but maybe we'll push it past the time I'm traveling. We'll see how it goes.
Well, too, if we have to, I mean, like, even if we have to like take like a week somewhere or, you know, like that's on the books as well. If we have like, we're really close to getting, I mean, we still have some pretty extensive chapters to get through.
Yeah.
I mean, we only have 1, 2, 3, 4, well, I guess 6 chapters, and these are probably going to be pretty advanced chapters. So, yeah, who knows? We'll just play it by ear right now, and then we can kind of reconfigure if we need to, and adjust the schedule as needed. We're not on a deadline, so I'd rather us learn the material or dig into it a little bit more than just trying to like speed through it, and just so that we can get through it.
Yeah. Are there any questions about what we did so far about the quasi-quotation?
I like the idea of injecting. That makes a lot more sense to me.
Yeah, it really tells you what it does.
Yeah.
Like, because it used to be like before, it used to be you'd have to use the functions like unquo, quo. And so like that just makes more sense with these like other operators that are provided to us. And I think the terminology is a lot more clearer and succinct, and it makes a lot more sense.
It's evocative.
That's a great word.
And I also like seeing the ASTs too, because like when I first like read through this, like because at first I thought like, oh, I can handle metaprogramming like a long time ago, and I would dig through metaprogramming like the chapters, like read them by themselves. But like it really helps to understand the AST, because the AST really like those abstract syntax trees really show.
Yeah, I love
Give
that
you a good idea what's going on. Like when you first look through the book, you're like, oh my gosh, these things are like terrible. But then once you like actually see them, they're actually really helpful to see how they actually work.
And they're also like, I mean, I still need to catch them a bit. But they're also not like even as insanely complicated, at least like in our world, right? Like even just like looking at them and manipulating them aren't horrific. Like I looked at a little bit in like Python, and I was like, okay, I'm not doing this. Like it's like what it outputs. I'm like, okay, we're never using this package ever in Python. But with R, it's like pretty easy. It's a lot of the same operations that we're all familiar with, like vectors and stuff that just apply to ASTs, which is like pretty powerful that you could just like have that, like in the language.
Yeah.
Yeah, we mentioned that a little bit last week. Like I think you said, Ron, like this is like one of the only languages that gives you this much like flexibility to like use the AST. I think you shared, I think Java or JavaScript. I know, or was that John?
John talked about JavaScript. Yeah.
Yeah. So it's a nice feature.
Yeah. There was a time when a lot of people were doing using eval and JavaScript as kind of shortcut things, but that's frowned upon now, as obviously being very dangerous from a security point of view. Just like you probably should never use, like you said, you should never use that parse thing and then immediately evaluate something, because you're just opening yourself up for some kind of code injection attack, right?
Yeah,
at least injection. At least not in any public facing code, which is, I guess in R is not as big a risk, but you never know where your code sneaks into some shiny package, some shiny thing your coworkers are working on.
Yeah, that's a good point.
Yeah, and you know, the other thing is like, you know, just when Hadley like wraps functions within functions, like that's where it gets like a little challenging for me, because like I can't see the diagram of how these all things are related. And so like when I go through it, I'm like, okay, so Hadley's wrapping it in this, wrapping it in this, doing this. And then like when you work it through your head, you're like, okay, I have to know all these layers.
Yeah. And
so it's like, dang, this is like challenging stuff. That's like the hardest part of this but at the foundation, it's not too challenging. It's just expressions, and you're just you know, inspecting, modifying, and, you know, evaluating those expressions. And so
yeah, it's like a pretty simple idea, just like wild. I don't know. it's definitely complicated, because like I don't get this like fully. But like, I mean, the idea is like, right, like you said, it's like pretty simple. You're just manipulating some code. That's really it. I mean, that's really it.
I think like if like I have to go back to like chapter 17, like the big idea, because that's like my anchor point. It's like, okay, if this is getting too complicated, go back to 17, reread this, and it's like, okay, it's not this challenging. It's just when you apply it in different contexts, it becomes challenging.
Yeah.
By the way, I know we're out of time, almost, but we're out of time. It's one quick thing. When also looking at the R-Lang documentation, he talks about this embracing operator, which is not discussed here. I don't know if that's a new thing.
Oh, yeah,
or not.
Yeah, that's a new one. I've used it like a bunch. Like let's say you have, you know, maybe you have like, you're doing some group by operation and you want to like summarize some statistics, right? And you just want to like pass the column name. So it's like, it's pretty similar to injection. It's just a more I would say like more user-friendly operator. I would be lying to say if I like fully knew the differences between like the embrace and the inject one, but to me it just seems like a bit more of like again like a friendlier way of injecting.
Yeah, I think it's one of those things where it's like how many users are actually going to like fully understand metaprogramming when like you just have this basic operator that helps you do what you want to do, and that's apply tidyverse stuff inside of functions. And that's where I got introduced to that, like the double curly bracket or whatever they call it now.
Yep.
Embrace.
And then go ahead. Embrace. And then like the colon equal sign, like if you are writing a function with like the select dplyr verb, or no, the rename dplyr verb, you can use that to pass in like a new variable name with your function.
Yeah.
So
or you can use it with like string R. If like maybe you're like in a mutate call and you're like, well, I need to create all of these like column names, you can use them. In Python, they call it the walrus operator, and I actually like that name a lot because it does look like a walrus. Right, you can just like use that, and then you can just like create a bunch of columns. Because I think it's like the string blue, if I remember correctly, that you have to like use that.
Isn't there a walrus operator in R too? Didn't Ryan mention that last time?
Oh, it's in
I think it
data
is that one.
table. Yeah,
Oh,
there's
data
in
table,
yeah
that's
data
right.
table, which it could also just be in. It could just be in base R for all I know. I'm not entirely sure, but like I know in data table you can use that operator. Oh shoot, I want to say it was to like create column names and maybe a bunch of other stuff. My like data table is like super rusty. Used it at my last job for a little bit, but like I don't fully remember.
I don't think looking at the syntax documentation, I don't think the walrus is part of like base. I don't know. I throw this at Stone because Stone, you're the base expert here. So
I don't think it's in base either.
Yeah, because looking at the syntax docs, it doesn't look like it is.
Yeah.
Yeah, it's and you see this stuff sprinkled, like anytime you see this stuff sprinkled, like anytime you use tidyverse stuff, like you see the metaprogramming stuff sprinkled in it.
Yeah, you do. That's why I've seen the bracing before. I'm like, wait a minute.
Yeah.
It says it basically combines enquo and splicing. So
yeah.
I don't know much about enquo yet either. So that's next chapter. So then I will learn.
I don't either. The unquo, quo, that stuff.
Oh sure, yeah.
I have abused that many times trying to get stuff to work. So
sure, yeah, you could do that.
It'll work.
A lot too. Like, let's try putting that in there. Yep, that made it work. Okay, let's move on.
It's like, what does it do? But doesn't work. It doesn't work.
I've got the slide made for my PowerPoint presentation or whatever, so that's all
my greatest fear is like I'm gonna learn what it actually does, and then I go back and be like, oh no.
Yeah, right. What did I do?
This is not good. So yeah, I have definitely abused quo and unquo before. So I think now it's the time to actually learn it. So, all right, well, cool. I appreciate everybody jumping in.
Yeah, thanks.
So
appreciate
yeah. Well, like I said, I really appreciate everybody being flexible with me. And so I'm glad we were able to get it in, and we'll plan on next week. So we'll see everybody.
Right. See you then.
All right.
Bye, guys.
Yeah.
See ya. Bye-bye.